Let's talk a little bit about limits at infinity. And what I mean by that is in the past we've had the limit as x approaches some c, which we've called a constant number, of f of x. Now let's take a look at what we mean when we say something like the limit as x approaches infinity of f of x. And for polynomials, we have a pretty straightforward rule, and that is the degree of the polynomial is going to drive where your limit at infinity is going, and specifically the highest power of a polynomial. So for example, if I have x to the fourth plus x cubed plus x squared plus x plus 1, this here is going to be the number that really takes off. When we plug in a really high number, for example, when we're looking towards infinity, when we plug in a really high number, that term is really going to dominate the other ones. And we have a pretty simple rule that we can put into a table. Let's do degree leading coefficient x to infinity, x to negative infinity. Let's make this a table. So if our degree is even and our leading coefficient is positive, think about that for a second. Let's take x squared. Let's take x to the fourth as our example. It's already circled. I have x to the fourth. If I have a positive number that I'm plugging in, x to the fourth is going to be very positive. If I plug in 2, for example, x to the fourth is 2 times 2 times 2 times 2, which is 16. And if I plug in a negative number, like negative 2, I'm going to get negative 2 times negative 2, which is positive 4, times negative 2, which is negative 8, times negative 2, which is positive again, positive 16. Because a fourth order polynomial looks something like this, where we might have a couple bumps. It looks kind of like a W sometimes. A fourth order polynomial, as we go towards positive infinity, is always going towards positive infinity. And as we go towards negative infinity, it's also going towards positive infinity, And so no matter what, if our leading coefficient's positive and our degree is even, it doesn't matter. Our limit as x approaches infinity is going to be infinity. Our limit as x approaches negative infinity is going to be also positive infinity. Now, for the same reason, if our degree is even and our leading coefficient is negative, we get the same result, but we flip the graph. So a negative fourth order polynomial, looks something like this, where the graph is just flipped. So no matter how you hash it, you're going to get negative infinity. Negative infinity. Now it gets interesting if we have an odd power, because remember, an odd power, for the best example is, let's do y equals x to the third power. Negative values plugged in are negative. So we get something that looks like this. Positive numbers come out positive, negative numbers come out negative. An odd power can tend towards negative infinity. So if we have an odd degree, let's call the leading coefficient positive. Then as x goes towards infinity, we are going to go towards positive infinity. As x goes towards negative infinity, though, this time we're going to go towards negative infinity. And then if we have an odd power and a negative leading coefficient, you can again think of that as flipping this graph here. We just flip the signs. We get negative infinity as we go towards positive, and we get positive infinity as we go towards negative. And so that's a table, but it's never too easy to understand just from a theoretical table. So let's look at a couple examples. Let's look at the limit as x goes to infinity of a few functions. Let's look at 4x to the fifth minus 3x cubed plus 2. Let's look at the limit as x goes to negative infinity of 4x to the fifth minus 3x cubed plus 2. Let's look at the limit as x goes to negative infinity of that same function, 4x to the fifth minus 3x cubed plus 2, multiplied by x cubed. And then maybe the limit as x goes to negative infinity, I don't know, of something like x plus, let's do x squared, minus x to the 12th. So in the first case, we have a function where 4x to the fifth is really the the only term we care about, because when these numbers get really big, that one is going to get bigger much faster than these two. It's going to dominate the end behavior of the function. And as we plug in really high positive numbers, we can kind of see that this is going to get really high and positive. Even if you plug in a low number like 5, this is already going to be a pretty large number. So we're going to be tending towards positive infinity. Here the leading coefficient is positive, and the power is odd. Odd power, positive leading coefficient, we're going to tend towards infinity as x tends towards infinity. And that's how we read the table. Now, as we tend towards negative infinity, we're still going to look at this same term, and we're going to say as we tend towards negative infinity, we are going to get a negative number, because a negative number to an odd power is negative. It's going to be very negative. It's going to be a large number in the negative direction. And so we're going to tend towards negative infinity. Now in this next case, we kind of have a different problem, but it's being masked. So here, our biggest term is once again the 4x to the fifth, but we have a product. So let's multiply that out. This becomes 4x to the eighth minus 3x to the sixth plus 2x cubed. And now see what happened. Our power on our x switched from odd to even. So now we have an even powered function with a positive number out front. So as we tend towards negative infinity, you can already see if I plug in negative 1 here, I'm going to just get 4 for that term. If I plug in negative 2, I'm going to get something really, really positive. So this one is actually going to be positive infinity. And we see that up here. We have an even degree, we have a positive leading coefficient, and so it doesn't matter if we're tending towards infinity or negative infinity, they're both going to be tending towards positive infinity. Now the last one here is just to show you, we're not always looking at the first term. We're looking at the term with the highest power, and in this case, that's going to be this negative x to the 12th. So we really care about the negative x to the 12th, not the x. So you have to be careful about your ordering of these polynomials. And we see that we have a negative number outside of an even-powered polynomial. So no matter what we plug in, whether it's negative or positive, we're going to get a positive number out of this, but then it's being multiplied by a negative sign. So this is always going to be negative. So the limit of x, as x approaches negative infinity, is going to be negative infinity. And so that's how we deal with these functions, these polynomials. One difference here is, moving forward, what if we have something like this? The limit as x goes to infinity of 1 over x squared, 1 over a polynomial. Well, the limit as x goes to infinity of the polynomial x squared, the limit as x goes to infinity of x squared, we now know is going to be infinity. And so the limit as x goes to infinity of 1 over x squared should be 1 over infinity. And when we're dealing with limits, we care a lot about what we're approaching, not the exact value. So 1 over infinity doesn't make much sense, but 1 over a very large number is approaching 0. So we can find end behavior limits of fractions as well using the same rules as the polynomials, adding the logic that if you have a really big number in the denominator, it's actually a really small number. And so we can formalize that rule by saying if n is a positive integer, then as x goes to infinity, 1 over x to the n equals 0, and the limit as x goes to negative infinity of 1 over x to the n is also 0. Now let's look at some examples where the limit as x goes to infinity or negative infinity might actually not even be infinity, 0, or negative infinity. It might not be a trivial answer. And let's look at the function, the limit as x goes to infinity of 6x to the 5th plus 2x over 3x to the 5th plus 4x squared plus 18. And if I'm looking at this function, I want to know the limit as x goes to infinity. So when I get a really big number, what's going to happen? Well, on the top, I'm going to guess something that's like infinity. But on the bottom, I'm also going to guess something that's like infinity. And so our question becomes, well, what is that thing? What does that mean, infinity over infinity? So let's look at this by dividing both top and bottom by the same thing. I'm going to divide both the top and bottom by the highest powered term. And then it should be pretty clear what's going to happen here. The limit as x goes to infinity, instead, I'm going to divide everything. Let's divide everything by x to the 5th. So our first term, 6x to the 5th, is just going to be a 6. Our second term, 2x divided by x to the 5th, is going to be 2 over x to the 4th. In the denominator, our 3x to the 5th is just going to be 3. Our 4x squared is going to be 4 over x to the 3rd power. And our 18 is going to be 18 over x to the 5th power. Now, what's going to happen as x goes to infinity is this term here, x is going to get really, really big. 2 over something really, really big is going to get really, really small. It's going to get infinitely small, which is something we call 0. So we're going to get 6 plus 0 over 3 plus, the same thing's going to happen with these other two terms. 4 over something getting really big and 18 over something getting really big are also tending towards 0. And so our limit here is actually just 6 over 3, or 2. Which means this complicated function, as x goes to infinity, let's say as x goes to infinity, y is 2. I don't know what's happening with this function, but at some point we're going off to infinity and we're going to be approaching the value of 2. That's what we just figured out here. And what we saw, let's go back and look. What we saw was, what really matters is, again, these leading terms. So we only ended up needing the 6 and the 3, the terms with the highest power. And that's going to be a theme here. So we could have just solved this problem by looking at the limit as x goes to infinity of 6x to the 5th over 3x to the 5th, and it would have been the same limit. And we call these auxiliary functions. Auxiliary functions. And we can always use auxiliary functions to better understand our problems. So I'm going to put down a formal definition here, which is just if the limit as x approaches infinity of f of x equals some value L, where L is not infinity or negative infinity, L is a finite number, or the limit as x approaches negative infinity of f of x is that L. We say the line y equals L, which we see here, we got 2, and so we have this line y equals 2, is a horizontal asymptote of the graph f of x. And all that means is at some point, our graph f of x, at specifically when we're going towards infinity or negative infinity, is going to get infinitely close but not touch the line y equals 2. Okay, let's look at a few more examples like this. Let's look at x to the 4th minus 2x cubed plus 13x over 7x squared plus x to the 6th minus 4x to the 8th, and we'll call that f of x. Now I want to know what the limit as x goes to infinity and the limit as x goes to negative infinity is of this function. So let's start with the limit as x goes to infinity. We are going to need the terms with the highest power from the top and bottom. From the top, it looks like that's going to be x to the 4th. On the bottom, it looks like it's going to be negative 4x to the 8th. And as we go towards infinity, we see that the bottom is going to grow much faster than the top. We could even simplify this function. 4x is on the top, 8 on the bottom. We're going to get 1 over negative 4x to the 4th on the bottom. And as x gets really big, this is going to tend towards 0. Now the limit as x goes to negative infinity, as x gets really big, again, this is also going to tend towards 0. So if our powers don't match up evenly, for example, if we have a higher power in the denominator, we're going to approach 0. What if we had a higher power in the numerator? What if we had the function f of x equals negative 2x to the 7th plus 3x to the 6th minus 1 over x to the 6th minus 3x to the 4th plus 100? Well, we look for the limit as x goes to infinity of negative 2x to the 7th this time, that's our highest power, over x to the 6th. And this can be simplified to negative 2x. So as x goes towards infinity, we are getting a really big number multiplied by a negative sign. So we get negative infinity. In this case, the limit as x goes to negative infinity of negative 2x is going to go in the opposite direction, because we're going to get a really, really small number, something really negative, but multiplied by negative 2 is going to give us positive infinity. And that is our limits at infinity.